Okay, so supposedly this is recording at this point. All right. So what I want to take a look at today, and we're going to be doing a lot of problem solving. So for those of you that were not here at the very beginning of class, make sure you have a pen and a piece of paper or some sort of digital tablet or something that you prefer to take notes on. Okay, we're going to go over two things. The first one that I want to discuss is part of the chapter material, but it's also something that is going to be important when you're doing your lab for Friday and the next lab for next week, which is called the 5% rule. So we have worked with equilibrium equations so far where we either can get a shortcut where we take a square root of everything, or we're forced into doing a quadratic equation. And many times it turns out that we have to use a quadratic equation. So there is another shortcut, which is called the 5% rule. That's the first thing I want to go over today. I want to explain what it is and how we utilize it, because it can save a lot of time. And then the second thing that I would like to discuss, if we have time, is to start going into what's called polyprotic acids. So we're going to look specifically at an example of a diprotic acid to start, because that's easier than a triprotic acid. But these are acids that have more than one acidic proton that they can give up. So an example would be H2SO4. It can give one proton and become HSO4 minus. And then that conjugate base in itself can be another acid. It can give off the second proton to become SO4 2 minus as the second conjugate base. So we need to take a look at diprotic and polyprotic acids and how to calculate equilibrium concentrations for those, because they are far more complicated than just doing a single equilibrium setup. All right, so that is the goal for today. I'm going to start screen share. Now, I will pop in. If you have a question, it's going to be best to use your microphone, because while I'm working through this, I'm going to have my whiteboard up, so I'm not going to be able to see the chat as readily, but I will try to pop in and check on it every so often. Okay, so let me share. So, can everybody see the whiteboard that I currently have on my desktop? Okay. So this is where we're going to be doing the work. So you should be able to follow along as I work through this here. All right, and let me put this up top. All right. So again, if you run into a question, you have a question, go ahead and speak up. And I will tell you, parts of this lecture are going to be abbreviated in the fact that I will not fully solve the quadratic equations on camera. Now, the reason for that, and you can do it yourself later, is because we're on a timetable and it takes a very long time to write out entire quadratics and work through them. So I'm going to basically be giving you the solved answers for the quadratics when we come across those points. Right? So the first thing that I want to talk about here is the 5% rule, and there's a question set up, right? But we're going to talk about weak acids just for a second before we start solving this question. So weak acids, which is primarily what we're dealing with in this chapter, are going to be in equilibrium. So a strong acid is not going to have much of an equilibrium because it will ionize 100%. But a weak acid is going to have a relatively small concentration of hydronium ion relative to the initial starting concentration, because we don't expect all of it to dissociate 100%. Okay, so what that means is that if I were to draw a general acid-base equation, I can say that a weak acid will be in equilibrium with, and you can use H plus or H3O plus, those are used interchangeably, right, plus its conjugate base. And all of these would be in an aqueous state when we're working with them. Now, keep in mind there would be water here if it's H3O plus, but I'm leaving that out because the water in general is not going to be contributing to Ka values. So the premise with a weak acid is that the concentration, now this is relative to one another, over here is large, and anything that we find over here is going to be small, okay? So when I say large, it doesn't mean that this number has to be incredibly large, but HA, the concentration of HA, should be large relative to H3O plus, because a weak acid should primarily be residing as an acid, not as hydronium. That's what makes it weak. It's not able to force the equilibrium all the way to the right. Okay? So this is a very important premise that we want to understand as we're moving forward with these types of equations. Right, so now what we're going to do is we're going to take a look at this problem. So it says a weak acid, which we're labeling as HA, has a concentration of 0.5 molarity and a Ka of 7.1 times 10 to the negative fourth. Find all of the equilibrium concentrations. So the main point that I want to do here, this is going to be an ice chart type of problem, is to show you when we get finished with the ice chart how to use the 5% rule. Now, if you've been reading in your book, if you've been following along, this is something that you should have been exposed to, but we're going to work through it right here in case you haven't. So the first thing that I would need to do is set up the general equation like I just had. So it's going to be HA, which is aqueous, is going to be in equilibrium with H3O plus, aqueous, plus the conjugate base, aqueous. All right. Now that I have that, I can go ahead and I can start setting up my ice chart. So I have ice, initial, change, and equilibrium. So the problem tells me that the initial concentration for the acid is 0.5 molarity. That means at the very start, none of it has been dissociated or ionized. Now the change here, because this is monoprotic, meaning it only gives off one proton, all of the balanced equation is 1 to 1 to 1. So in a case like this, I'm going to have minus x plus x plus x. Now, when I get to the equilibrium state, it should be 0.50 minus x, x, and x. So everybody should be able to do this even without my help at this point. This is something we learned in the previous chapter. You've been tested on it. You've seen it in homeworks and quizzes. So I would expect that you're okay up to this point. Now, what you would have to do, we have a Ka value here. It's 7.1 times 10 to the minus fourth. That is the equilibrium constant for this acid. So what I need to do at this point is set 7.1 times 10 to the negative fourth equal to what this is going to be. So the products are the hydronium and the conjugate base, H3O plus and A minus. Each of those are represented as X when I am at equilibrium. So I can simply put X times X, which is going to end up as X squared. Okay, and then at the bottom here, I'm going to end up with 0.5 minus X. Now, if you take a look at this, this is headed towards a quadratic because we're going to have an X squared at the top, and at the bottom, while we don't have to do any factoring, we have an X value. So anytime we have an X squared and an X value, we're not going to be able to utilize those in one technique. Okay, so this is where the 5% rule comes in. If you were to originally say you were going to solve a quadratic. And what the 5% rule says is that X is going to be small because, like we said at the beginning, a weak acid should generate relatively little amounts of H3O plus. So H3O plus, which is represented by X, should be fairly small compared to the initial concentration of HA. So if I say HA's initial concentration is 0.5 and X is going to be relatively small compared to that, then I can set up a general assumption where I say 0.50 minus X is going to be approximately equal to just 0.50. And that is under the assumption that X is so small that when I subtract it from 0.5, I'm going to get 0.5 and some small amount of change back way down here in the decimals, which when I round with significant figures just returns 0.5. Everybody with me so far? All right, feel free to break in if you have a question at some point. So what we'll do is we move forward and we say, all right, let's toss this out and assume that it's very small. Now that doesn't mean you toss it out at the top, right? So what you end up with is 7.1 times 10 to the negative fourth, and that would be equal to X squared over 0.50. So now all I have to do is some algebra. I multiply both sides by 0.50, and if I do that, I would end up with x squared equal to a value, and I can take the square root, right? So in that case, what I would have would be x squared is going to be equal to 3.5 times 10 to the minus fourth. Okay? That came simply from multiplying 0.5 to each side. So what I need to do now is take the square root, and I can do that because I don't have an x over here anymore. It dropped out because I assumed it was small. So then I can get back x equals whatever this value is. So when I take the square root of this value, I end up with 0.019 molarity, and I was able to skip over the quadratic. I didn't have to set my quadratic up. Okay, now, this would still be quicker if you were doing it by yourself. I'm dragging this out a little bit because I'm explaining it here. So you have to test the assumption. This is where we get the term 5%. And the question is x going to be less than 5% of the initial concentration, which was 0.5? Because if it's less than 5%, we can say that it's small enough that it would be negligible. If it's greater than 5%, then you need to go back and solve your quadratic, right? So the way that I would do that is I would simply, it's almost like a percent ionization. I would say, all right, I have 0.019 molarity, right, which is x, over 0.50 molarity. I need to times that by 100 if I want to check the percent, because it'll come back as a decimal. And I end up with 3.8%. And you can put these numbers into a calculator and just confirm as we're going along. Okay? So because this is less than 5%, I get a pass here, and I do not have to solve my quadratic formula. I can move forward. Right? So then it initially wanted, the question said, let's find all equilibrium concentrations. So to find all equilibrium concentrations, I know that H3O plus, as well as, so I'm going to put and the conjugate base, are equal to 0.019 molarity, right? And then the HA at equilibrium, if I go back and I check my equilibrium value in the chart, was 0.5 minus x. So here I need to take 0.50 minus 0.019. Okay, and that should come back with 2 decimals, which would be 0.48 molarity. And so there's the answer for HA, and there's the answer for H3O plus and A minus. Right? So this is a very important technique. It takes all of 2 minutes to solve the algebra, and if you are under the 5%, you get to skip out on the quadratic equation. Okay. Now, keep in mind, this will not always work. So I'm about to show you an example where it wouldn't work, and we would have to go through that. Okay, so let's go back here. I'm going to erase the beginning portion. And we're going to take a look at an example where it may not work. Okay. So now I'm going to make one change here. I'm going to say that instead of it being 0.5, let's make this weaker so that the chance of x being less than 5% is not going to be as probable. So now I'm going to make this 0.050 molarity. We're going to reduce the concentration that we're starting with. Okay. So I would go through the same process. I would set up the same ice table, except the 0.5 would now be 0.05. Okay. And when you end up with this, you solve for x, okay? So you would go through that process again, where you make it negligible, you cross it out, and you're gonna find that x is equal to 6.0 times 10 to the minus third. So again, if people are asking where this is coming from, because I just suddenly put x up on the screen, I'm skipping some of the math because I have a lot to teach you here, okay? So where that came from was if I set 7.1 times 10 to the minus fourth equal to x squared over 0.050. If you solve for x here, right, and we get rid of the minus x that was here, assuming that this would be small enough, this is the value you find for x. So now I'm jumping forward, right? And I'm checking my assumption. So here I would say this is X. The initial concentration was 0.050. So is this acceptable? And you would need to, multiply this by 100. Okay. You solve for this, you end up with 12%. So this would be a case where you would have to say, nope, the assumption was not correct. This would be marked with a fail. And you would need to then go back and solve the quadratic, right? Now, the quadratic for this right here, including the X, so the minus X is back in play here because it was not smaller than 5%. Okay, if you put this together and you do your algebra, moving it up and multiplying 7.1 times 10 to the minus fourth, factoring that into 0.05 and X, what you would end up with is the following: X squared plus 7.1 times 10 to the minus fourth X plus, minus 3.6 times 10 to the minus fifth. That would be equal to 0. So all I did here was I set this entire equation equal to 0 through algebra, and I came up with the equation I need for my quadratic equation. Now you solve through the quadratic, you're going to get two answers. I'll let you do that as you work through on your own time. Okay, the answers that you should get are 5.6 times 10 to the minus third molarity and negative 6.4 times 10 to the minus third molarity. This one becomes an obvious toss out because we can't have negative concentrations. So 5.6 times 10 to the minus third is going to be the value that X would be equal to. And then you just go through and you solve your equilibrium concentrations using that value. Okay. So we've gone through an example where the 5% rule was effective, and we've now seen an example where it failed. We had to go back and utilize the quadratic formula in order to find this. Okay, so I'm going to pause here before I move to diprotic acids and ask the class, are there any questions in regards to the 5% rule, how it's applied and why it's useful? Okay, so the next thing that I'm going to do then is move over to diprotic acids so we can take a turn looking at that. All right, so the first thing I want to do briefly is discuss diprotic acids. So the thing about diprotic acids, and you can get into triprotic acids like H3PO4, but we're going to start with di because this will be complicated enough. When you have a diprotic acid, it means that it can give off 2 protons in solution. So you have 2 removable protons. Each time you remove a proton, you have a different Ka value. So we are now starting to handle acids that have multiple Kas instead of 1 Ka. You have an equilibrium constant for the first proton at equilibrium and an equilibrium constant for the second proton at equilibrium. Now, let's visualize this for a second. I'm going to use carbonic acid here as an example. So you have H2CO3, aqueous, and this would be in equilibrium with HCO3 minus plus, and I'm just going to put H plus here instead of H3O plus. Okay? Again, they can be used interchangeably. All of these should be aqueous. All right, so there's the first. Now you have to keep in mind that this right here, this conjugate, is still an acid. It has another hydrogen proton that can be removed. So I then have to say, all right, I can now make this the new acid. And in making this the new acid, I have a second equilibrium in solution, which is going to be the carbonate ion as a product. And again, the acidity content, right? So if you take a look at net ionic, we're talking about dropping out this base, conjugate base or conjugate acid in the second line. And it's really that the carbonic acid can dissociate to some extent to give hydrogen and CO3 2 minus if it were to completely dissociate. Now, because it's weak, we know that's not going to happen. A certain amount of the first proton will dissociate, a certain amount of the second proton will dissociate. So I have to give two separate Kas in each case here. So Ka1 is going to be for the first equation, and that is going to be H plus and HCO3 minus over the H2CO3, carbonic acid itself, right? And then I would say that there's a second equilibrium in solution, and that equilibrium is going to be equal to H plus and the carbonate anion over the conjugate acid base, which is HCO3 minus. Okay, so these are two different equilibrium constants for two different sets of reactions because the acid can come apart twice. So when you have a situation like this, and this rule that I'm about to mention is going to be universal. The first Ka, the removal of the first proton, will always be easier than all the subsequent protons. So that is to say the first proton will be the most acidic, and therefore its Ka value will be the highest of the bunch, meaning it's the most acidic. All right, so as we continue, we would expect Ka2 to have a smaller value than Ka1. In an example where I would have a triprotic acid, I would expect Ka1 to be the strongest, then Ka2 would be a smaller value, and Ka3 would be even smaller after that. So the actual values here for Ka1 for this reaction would be 4.2 times 10 to the minus 7th. That's the Ka for the first proton removal. And for the second proton removal, it would be 4.8 times 10 to the minus 11th, so significantly smaller than the first proton that was removed. Okay, so this is this brief section here before we actually start solving the ice chart and the equilibrium values. I want people to realize what a diprotic acid is and the fact that we now have two different reactions technically going on at equilibrium, and each reaction has to have its own constant, and each of these are going to have their own amount or concentration at equilibrium. So this becomes more complicated because I'm going to be setting up multiple ice charts. The first ice chart will be for Ka1, and the values that I obtain from Ka1 will bleed into a second ice chart for Ka2, which I will then finally use to solve all of the equilibrium concentrations. And so the problem here says a sample of oxalic acid has a concentration of 0.1 molarity. It has a Ka1 of 6.5 times 10 to the minus 2 and a Ka2 of 6.1 times 10 to the minus 5. Again, notice that the Ka2 is always weaker than the Ka, the first one. And it says find all equilibrium concentrations. So that's going to be the goal, and this will take us up to close to quiz time. Okay, I've got about 20 minutes and then a little bit of buffer time to give you guys for questions and getting ready for the quiz. All right, so let's take a look at the oxalic acid. So oxalic acid can be the first equation, which is all I'm interested in right now, can be represented as the following. It's going to be 2 hydrogens plus the oxalate anion. This is going to be in equilibrium with the acid content plus the conjugate oxalate. So I'm going to have HC2O4 minus, because it's only lost 1. Okay, and this is what I'd be working with. So let's set up the ice chart and solve for Ka1. Okay, and while we're doing this, we will implement the 5% rule so you get more exposure to that. So when we start here, we have 0.10 per the problem's information, 0 and 0. The change is going to be minus x plus x plus x. And then the equilibrium is going to be 1 minus x. Again, nothing should be shocking here. X and x. Okay, so what I'm going to do, I'm going to take Ka1, which is given in the problem, and I'm going to set it equal to my equilibrium, and I'm going to go ahead and try the 5% rule and see if I can get away with it. So what I would do is I would say 6.5 times 10 to the minus 2 is going to be equal to, now I'm just going to abbreviate here, x squared, because both my products are at the top, each one of them is an x, and on the bottom, 0.10 minus x. So what I will do is I will assume x is small. I'm going to knock it out. And what I end up with then is using the 5% rule. So all I have to do is multiply 0.1 to the 6.5 times 10 to the minus second. That's just going to change the exponential placeholder. So I end up with 6.5 times 10 to the minus third, because I multiplied by 0.1, and that's equal to x squared. So now I can get rid of this square root. And if I solve for x, x is going to be equal to 8.1 times 10 to the minus 2 molarity. So the question is, does this follow the 5% rule? It may not, because minus 2 is a fairly large number, right, relative to that 0.1. So I have doubts here. Okay, I'm going to divide through by 0.1 molarity. That was the initial concentration. Multiply by 100. And sure enough, I am way off base using this rule. I end up with 81%. So that's a massive fail on trying to use the 5% rule. So now that I'm through with that, I know I need to head over and start with a quadratic. Okay, so what I'm going to do to save space, I'm going to remove what we just had here, but I'll keep the ice chart because this was a no-go. And I will go ahead and move over to my quadratic equation. So again, I'm going to be working with 6.5 times 10 to the minus 2, and I'm going to set that equal to x squared, and now I'm not going to drop out the minus x. I have to keep it in there because that rule failed. Okay, so if you were to put all of this together into your quadratic, which means you would be taking this value, okay, I'm not going to walk through all of this, but if I were to multiply each side by this to drop it out, that means I'm distributing the 6.5, right, over to this value here. So I can get rid of that. And then I'd need to distribute this value over to this when I multiply it on this side here. Right? And then I have to isolate the x squared and set it all equal to 0. So if you do that, you should end up for your quadratic with x squared plus 6.5 times 10 to the minus 2x, okay, minus 6.5 times 10 to the minus 3 with no x value there, equal to 0. Okay, so then you do your a, b, and c, plug it into your quadratic equation, and when you solve your quadratic equation, the usable answer, okay, so let's put here, okay, for the sake of time, we're not going to do this because we have a lot of work, but we solve the quadratic formula, and the usable answer you should find from that is going to be x equals 0.054 molarity. All right, so this is, we've just solved for x using the quadratic. So now I have part of the answer, but I do not have all of the answer because this is diprotic. So what I can say is that for Ka1 at equilibrium, the H plus concentration and the conjugate base concentration, because those were both set equal to x in the ice chart, those are going to be equal to whatever x is, because that's the full value at equilibrium. So both of these are going to equal 0.054 molarity, and then H2C2O4, which is the actual oxalic acid, is going to be equal to 0.1, which was its initial concentration, subtract 0.054 molarity, and you end up with 0.04. Okay, it would be 0.046, so you can round if you're doing your 2 decimal places to 0.05, excuse me. Okay, so approximately 0.05 molarity. All right, now I'm keeping this value here at the 0.46 because we can plug that in when we have the final answer if we need. All right, so now what we have to do is we have to go through the second part because this has a second proton that can dissociate at equilibrium. So now I have to say, all right, I'm going with the conjugate base as my new acid. That will dissociate to give off the second proton plus now the true base that has no protons left. Okay, all of these being aqueous here. So in order to properly solve this, I have to set up another ice. Now I need to reference what I had above in order to continue this. So the question is, what is my initial concentration of the HC2O4 minus ion? Well, I don't have that in the initial problem. I had to solve for it, which is right here, right? This value is 0.054 molarity. So I can say that this is 0.054 molarity. Okay. Now, here I cannot put 0 as well because I know that at this point in the equilibrium due to Ka1, I found a concentration for H+. So the concentration for H+ is 0.054 molarity per the answer above. Now this is 0 because I have not gone through and solved for the actual base yet. Okay. Now the change here, I'm going to put Y because we already used an X in the previous example. So what we'll do is you can pick out Z or any other letter you want, but we'll just do minus Y because we're going to lose some amount of this that we had in the Ka1, and then we will gain some amount here and here. So what is that going to give us in equilibrium? Well, it's going to start looking like a mess here. We're going to have 0.054 minus Y, okay, and then we're going to have 0.054 plus Y, and normally we just have Y or X here, or whatever value you're using, but the problem is we already have some amount of H plus from Ka1, and that carries over into Ka2. So we need to account for that when we deal with an additional amount of H plus that's going to be added to the first amount. Right? And that makes sense because if we think about H plus, it's the amount of H plus generated by the first acid dissociation and the amount of H plus generated by the second acid dissociation. Okay, so when we do that, what we're going to end up with is the sum of those two. So now we have to go back up to the problem because Ka2 is given here, 6.1 times 10 to the minus fifth. Right, so we come back and we say, I'm going to set 6.1 times 10 to the minus fifth, and I will set that equal to this entire setup. So it's the product, so I have to include the H plus there, which we said is 0.054 plus Y. Right? And then Y, that's from the base. And then the acid that is now monoprotic was 0.054 minus Y. Okay. Now, this is becoming a big mess, so I'm going to try the 5% rule again and hope that I can skip out on this. If not, I have to simplify all this and head to a quadratic. So when I make the 5% rule, I can say anything that is plus or minus Y drops out. So let's get rid of plus Y, let's get rid of minus Y. Okay. And when we do that, you now have a value of 0.054 on the top and the bottom. So that's nice because these then can also drop out with one another, right? And that means that Y will simply be equal to 6.1 times 10 to the minus fifth. Now that's good because this is a much smaller number than the first time we found X. The first time we found X was a larger number, okay, and it didn't cancel out. It was almost equal to the initial concentration. So you have to keep in mind your concentration here is not the 0.1 that was originally given. it's going to be the 0.054. Okay, and that's because if I look at this, this is for K2 or Ka2, which is this example right here. So this is the initial concentration here, whereas the initial concentration at the beginning was 0.1. So I just want to make that clear for everybody when they're testing. All right, so if I times that by 100, this has a better shot at working. And if you put that into your calculator, you should see that you end up with 0.11%, so less than 1%. So we are good to go. Thank goodness we don't have to simplify all of this jargon up here. And that means that Y is going to just equal 6.1 times 10 to the minus fifth, or it will equal the Ka2. So in order to bring all of this to a close, we had to, the initial problem, you don't want to lose track of this, okay? The initial problem said find all equilibrium concentrations. So that means we need to find the concentration of the oxalic acid, the monoprotic conjugate form of the oxalic acid, the H+, and the actual base form of the oxalic acid. We need the concentration for all of those. So let's go through that. The concentration of the oxalic acid, we didn't touch that in the second portion here. We found that in the we found that in the first equation, the first portion, and we said that it was equal to 0.05, right? Molarity. Okay, now when we come and we take a look at the monoprotic, it's the HC2O4 minus, and the concentration for that is going to be, okay, at equilibrium equal to 0.054 minus 6.1 times 10 to the minus fifth. Okay, now that comes from right here. At equilibrium, we have this value. All right, now this value, if you take a look at this, 0.054, we just said that it's only 0.11%. So that means that this value is so small that when I subtract it from 0.054, it's going to drop out. I'm just going to get this back. So this is the concentration of the monoprotic conjugate. Okay. The same thing is going to be true of H+, and the reason it's going to be true of H+ is that H+ at equilibrium is going to be equal to 0.054 plus Y, right, which was up here. So again, if Y is this very small value, it doesn't contribute overall, and H+ is equal to this. And then to finally conclude, we say what is the value of the base right here? It's equal to Y. Well, Y was equal to 6.1 times 10 to the minus fifth. Okay, I'm running out of room here, so excuse while I squeeze this in at the bottom. But this right here would be C2O4, 2 minus, and it will be equal to 6.1 times 10 to the minus fifth. And now we have solved for every single species at equilibrium. So you can see this type of problem, compared to what we are used to, is far more complicated than just solving for a single ice. Even a single ice with a quadratic, we even did that here and then had more work on top of it. Okay, so needless to say, diprotic and triprotics are not quiz material. They could potentially be a test material, but if I did one on a test, I would need to factor in the amount of time this is going to take you, which means I would have to put more points weighted on this so that there wouldn't be as many questions to get through, because this would be taking up a lot of time. And I obviously would break that apart into steps. I would say you get a certain number of points for each concentration you find correctly. I'd give you points for each of the ice boxes set up correctly, and so on and so forth. All right, so I'm going to stop the share at this point. I'm just coming back to the classroom. So what I want to do, because it's 1:12, all right, we are going to open up the floor to any questions you may have, and then at least by 1:20, if I'm still answering questions, I want to stop and give everybody 5 minutes to get their calculator, get fresh pen and paper out, because then at 1:25 we have the quiz. And I also want to reiterate, you may need to use the 5% rule on the quiz, but I for sure am not putting any diprotic or polyprotic questions on the quiz. That's too intense for a 20-minute session. It took me almost 20 minutes to explain that to everybody. All right. So that being said, I'm going to go ahead and open the floor up to questions here.
Is the cutoff for the 5% rule exactly at 5%, or it can be a little above it where it still counts? So if it's like 5.1%, is that still negligible enough, or is it?
For the sake of the course, 5.1% is going to be considered inappropriate, and you have to solve the quadratic.
Okay.
Now, in real life, if you're moving through a laboratory situation doing work for somebody, I would say move forward. Don't worry about that. But we have to make a universal cutoff so that everybody's following the same rules, and that's the general agreed upon standard. Just like where do you make the cutoff for something being a significant value or not in statistics, we have to have agreed upon rules so everybody can agree. So yeah, technically, if I give you a problem and it's 5.1%, then I'm just being insanely cruel and I'm telling you to go back and solve the quadratic equation at that point. Okay, good question. Yep.
Is there a way to kind of like skip the 5% rule? Like, if the molarity is significantly small, like, I guess on like the first one you had it to like 0.50. Like, do you get what I'm kind of trying to ask? I can't quite find words.
I do. So if you realize that the initial molarity is very small, you can make the call yourself. How do I put this? You don't ever have to implement the 5% rule. It's there to help you. Now, in fairness, you have a lab coming up and they say do the 5% rule. So you can't skip that and say I don't do 5% rules, right? But on a test, if you are given an equation like this and you have to solve it, you can either just say I don't do it because I don't want to go back, I'd just rather solve the quadratic, or you can take a look, and if you have a good general feeling like, look, this initial concentration is incredibly small, and so the chance of the ratio of these two being close to one another is not going to work out, then you can just go ahead and drop that if you want to. That's based on your own call. It's not like it's going to hurt you. It could just only potentially make more work for you at the end of the day if it was a close enough call, and let's say it was 4.8% instead of 5% or something like that. But yes, you technically, if you are good with numbers in your head and you can see the value of the initial concentration as well as what X is coming out to be, and you know that it's not going to be worth your time, then you can just head straight into a quadratic. You're not going to get punished for doing that. Other questions? All right, if there's no other questions right now, then I'm going to go ahead and stop the recording at this point, and hopefully I'll be able to recover that while you guys are taking the quiz.